I'll try to come back before another 10 years goes by. I'll be talking about web APIs for the big science enterprise. And as much as I really like the interface, that Steve has been showing off, my thinking is really sort of what comes next, what comes after that, because the programmatic interaction with transfer of data, is something that ultimately is going to be stitched into your applications and into your workflows in ways that are more subtle and less blue, compared to the nice blue interface that they have there. So I just wanted to kind of let you know that at the outset, because my intent is not to really demo the interface or those sorts of things, but to hopefully say some maybe thought-provoking things that maybe you'll disagree with, and we can have interesting discussions later. Oh. So just a few words about the title. This talk is in some ways a extended analogy between the apparatus for science that was the cyclotrons and the particle accelerators and the software world where I live. And I see some glaring but hopefully resolvable sort of approaches to software and data in particular that I would really like to see changed. And so if you imagine taking away the software from almost any modern science project, it's a complete dependence on that sort of infrastructure that's there. And yet the way that it's developed and deployed oftentimes has a lot more to do with the picture you see here on the left than on the right. So this is Lawrence with his first little toy cyclotron, where he learned how to make ions do a little dance in a circle and go around and around and around. And that's all fine and great. That is where innovations come from. But the enterprise of science, in a lot of ways gets a lot more interesting when you can begin to move a lot of ions, right? And so if you replace ions with the megabyte counter that's on the Globus Online front page, I would posit that the types of science that we can accomplish really begins to change when that bandwidth of being able to move large amounts of data without kind of exceptional level of detail or attention to how it happens, that's where it really gets interesting. And so, for people in the software world who think, oh, we'll just do prototypes and then we'll let somebody else implement it, I would offer that it really is the sustaining, the maintaining, and the long haul that is what delivers science impact, right? And so I very much appreciate the direction that the Globus Online team has gone with this, because if they had stopped simply at the proof of principle that one can move data, that would have been sufficient to check the box in terms of a computer science research project, but it would leave the rest of the world really lacking for a way to seamlessly, efficiently, reliably move their data. So I'm very keen on how we can sustain their effort and try to make this a long-term sort of thing. So I wanted to reinforce this analogy a little bit by looking at the Large Hadron Collider, and we're lucky enough to work with two of the teams that are there in quite a bit of detail. And I would offer the following, is that their transition from looking at research networks, high-speed science networks like ESNet and CNIC and a lot of other things, has gone well beyond the research of proof of principle to show that the network is possible, that they've really built it into the DNA of their project at this point. So this evolution here is sort of in chronological order in terms of increasing expectation that the network and its bandwidth just work and be there. And that enables new science. That's how you get to ask new questions, is by obsoleting the old ones and by taking an activity that used to be heroic and making it commonplace. And so we shouldn't confuse, in my opinion, that transition between something being a researchy prototype to it being bulletproof hardened infrastructure as a boring activity at all. That is the guts of science overall. And so where has this led to? And there's a comparison here between Netflix and LHC. And I would offer that the comparison between the two is quite a bit more subtle than is one better or faster or whatever than the other. You know, they're each trying to accomplish different goals. They're both moving a lot of data and have kind of, you know, interesting worldwide data distribution methodologies. But they're towards different ends. You know, one is to make money, another is to discover how the universe works and to deliver on scientific propositions. So is whatever enterprise thinking you might have that you can sort of apply to dollars and cents, I would say that you know, consider applying some of that same thinking to the endeavor of science itself. And you can see that these are not reaching the same point, that Netflix and LHC computing are doing different things, and they're learning and showing off new capabilities in different areas. So when we think about data logistics and how scientists move data around, there's a lot of other activities. We're not the only people in the world who are thinking a lot about data and relying on data, but there are certain aspects of how science works that require certain capabilities that we will not find in that sort of dollars and cents world. So I want to give, this is the part of the talk that I like, because I get to talk about some of the science projects that I get to work with, which is why I like working at NERSC. So this is an example of a project which is trying to catch photosynthesis in the act. They're trying to look at the water splitting that happens in the photosystem 2. They're using a technique called diffract and destroy, which is they use one of the world's most powerful X-ray lasers to zap this photosystem with a short pulse of X-ray light. And in doing so, they sort of in a Bugs Bunny cartoon type fashion, they get a diffraction pattern on a detector very, very quickly, and shortly after that, the entire system vaporizes and is blown apart by the X-ray energy. But by doing this over and over again, they can take these very, very fine-grained snapshots of what's going on in photosynthesis. And this is really, you know, our first you know, real approach towards catching photosynthesis in the act. The splitting of water is where the interesting energetics really come about. This generates a lot of data, 150 terabytes per experiment. This is going only upward as detectors get faster and higher resolution. A good 10 years left on the exponential curve for this type of activity. It triples the traffic across our border when it happens. It's one of the reasons why the coupling between scientific facilities within the DOE complex is such an exciting area right now, because it's these interfaces where we, NERSC, ESNet, bring a capability that the spectroscopists didn't know that they had before, and new things happen. So. The second example that I have here is from the Advanced Light Source at Berkeley. This is looking at tomography and microdiffraction of materials. So, for instance, the pipe in a nuclear reactor, how do cracks begin to form in it? What sort of phases of crystallinity are involved in that? They take a sample of that pipe to the Advanced Light Source, they put it under this device, it generates many, many high-resolution images, each of which needs to be computed on in order to generate this sort of clunky image that you see here on the right. And the expectation that you know, scientists have developed over time is quite forgiving in the sense that they're okay going like 3 weeks between when they take the picture and when the film develops, right? And anything that we can do to shrink that time frame is a big, big win for science, and will only build greater expectations on the part of those scientists for what we can do, and what ESNet can do, and what all of us can do to make their data happen faster. The last example I have is one that's early on. There's this really in planning stages, but when something interesting happens in the sky, the current methodology to get people all over the world to point their telescopes at that interesting thing is our cell phones. They call people in the middle of the night and they say, hey, we saw something, you know, why don't you point your telescope over there? And as many of you who work around computers might might consider, there are better, possibly better ways to do that than just calling people all over the world. In 2011, the earliest ever supernova was detected, and this was crucially dependent on fast computers, fast networks, and unfortunately a lot of cell phone calls to get people to look in the right place. But something interesting happens. The sooner everybody can look at it, the better everybody is. So those are some examples of really the facility side driving new science that demands that high bandwidth data services like Globus Online and other things like that become reliable, ubiquitous, and just things that you can count on. So not a hero thing where you prove that you could do it once, but where you can really just make it happen. Okay. So now I want to try to say the things that people might disagree with. The first of which is a Mac or PC sort of view of the parts of the Office of Science that I interact with a lot, which is high energy physics and basic energy sciences. And these communities come into their thinking about data at different times for different reasons. And really, ultimately nobody, or very, very few people are fundamentally interested in data itself in these spaces. They're interested in physics and chemistry, right? And so, I've talked to a lot of people, and it's a generalization. I'm sure it's going to offend, whoever it offends. But, the HEP world is pretty prepared. They've been at this for a long time. They tend to have planning horizons that are further out. The beam lines that surround a advanced photon source or an advanced light source are smaller teams, more ad hoc, less long-term planning, and big data crunches that they're involved in right now. So the light source community is a fascinating one to work with right now because they're just coming into understanding sort of what's possible there. So the material I'd like to wrap up with is really about web APIs. And I'll say some things that are positive, and then I'll say some things that are negative. We're living in a time right now of huge, development of web APIs. There are, I think, 190 RESTful science APIs on programmableweb.com. So we're at a point now where we're having search engines to find the APIs that you might want to use, right? So this is good. It is good. And here are my thoughts on that, right? Which is that it's really REST that I think deserves a lot of the credit, and Roy Fielding in particular, for that. And if you're going to do enterprise discussions, I decided I would use all the Microsoft clip art that I could find, because that's the business world, right? So REST APIs are cool. Here's some of the kind of current state of where they are. And I included this, poor farmer guy here on the right, because it's not all fun and games. As anybody who's deployed one of these before, there's a lot of plumbing, there's a lot of nuts and bolts and nitty-gritty behind APIs, but the intent is to make them just super easy to use for consumers to come along and pick them up and use them. And there's this comment I make here: why are they all written by data providers? It's the people who provide data who are more often than not writing the APIs about how the data is exposed. That's okay, but it's a little asymmetrical because the people who are interested in the data, they have opinions too. So I would, in my most laudatory statement, say that REST APIs have really done some great things. They've magnified the value of some very expensive resources, and they have democratized science in the direction that Ian was talking about the 1% and the 99%. Is that we're going to get more science from more people in bigger and better ways by improving accessibility and by not having scientific resources, and I mean resources here in the REST sort of way, hidden behind cryptic or difficult interfaces overall. Going forward into the land of big data, as was described, this is going to be critically important. It's APIs that I think will be your only or main visibility into data sets that you simply cannot take with you. There's another element of data culture that I didn't get into here, which is that the idea that you feel secure about your data because you have a copy of it, right? Like you can hold the copy in your hand, with Dropbox and Gmail and all these other things. We are sort of learning to deal with remote data in other ways, and so these APIs are our eyes and ears and how we interact with that. I would encourage you to to check out the W3C group. There's a community group on HPC and the web, which is a group of, I think, 27 members now, who are looking at big data, science, web technologies, and how all these things kind of come together. I learned last night about that the OGF has considerable prior art here as well. So this is what this is the perspective I reach by not coming to GlobusWorld for 13 years or 10 years or whatever. I want to just say a couple words about Newt, which is this API for HPC things that we're using at NERSC. It tries to be really simple, and if you read the documentation on the web for almost any HPC center on the planet, it'll be this stuff. This is the stuff that people need to know how to do, right? So we said, hey, can we make an API that just does that stuff? Our figure of merit is that it has to be as easy as online banking. We've had a regular stream of high school and undergrad students who come in, and we tell them to do HPC, to make apps. And to the degree that they are successful in using their jQuery skills and other kind of basic web stuff to do things, that informs us about whether we're going in the right direction or not. So I think back to the are you a HEP or a BES sort of thing. If you need to explain the middleware stack to somebody, then you've already probably sub-selected a great deal of the potential scientific participants out of that 1%. So these are some examples. I didn't want to give a really technical talk, but the semantics of REST about getting and posting and putting and deleting, these apply to jobs and files and things like that, and all the sort of usual ways that you might imagine. Here's the kind of messy plumbing that the farmers like me and Shreyas and other people have to deal with underneath that, and so here's some of the moving parts that are involved. We view this as a complement to the command line, and one of the selection biases that you run into talking with people who are already computing at a computer center about whether a REST API is something that they're interested in is in part that they're already computing at a computer center. And so they've already crossed that activation barrier into the command line world. But we find that increasingly there are at least some parts that people would rather have operate more like the software as service type of niceties that we have in our daily lives, and so it will continue to be a balance between the kind of command line and the web. A lot remains to be done. And I wanted to say a couple things about that, again, invoking my Microsoft clip art here. These are some of the things that you might overhear between a computer interested person and a physical sciences interested person about how they can collaborate on data. And I'm sure there are many other sorts of gotchas and headaches that people can run into, but these are some of the ones that I think are definitely worth bringing to this group. I'm very interested in what solutions or other things people might have. And really what I'm getting at here is that people are kind of talking a different language, oftentimes about data, and that there's not a good meeting place for people to expose their data to one another, to share it, to test drive it, all that kind of stuff. The second kind of flip side to those is, from the physical scientist perspective, that anything that's really complicated, sorry, that's just that's not going to be an easy thing to do. If there's a steep learning curve to adopting a data methodology, in my decade plus of experience with it, it's going to find limited application. And again, I try to wrap up here with this notion that the way that APIs are written, as they stand right now, do not allow for the sort of flexible dialogue or negotiation between the parties involved. So, I just wanted to wrap up with one or two more slides here. I think I'm right at my time. Big data is not free. A lot of the economies in the world that handle computing or handle data or other things like that are things where you write a proposal, and if the science is good enough, then you get an allocation of millions of CPU hours or however much storage or whatever. And as the storage volumes go up, I think we do need to acknowledge the real costs of data, right? And so, if we're talking about petabyte data sets, making these as available as possible, that's exactly what we should do, I think. But we can't do that and at the same time acknowledge that it costs money, right? So if some random person says they want this petabyte of data, and there's a substantial cost to provide that, we should somehow balance into this those real costs. Likewise, I think we should make data discovery a priority, which is that we have these growing data sets and data resources that are out there, but we don't have good mechanisms to advertise data to one another. And if anything, data is the easiest product in the universe to test drive, I'm claiming. And so why can't we make that easier? Providing snippets of data, providing schemas that are flexible enough to allow deeper participation in data. And there's some more slides, but I'm out of time, so I'll wrap up there. Thanks.
Thanks, David.
Questions?
Questions? No questions? Oh, one in the back there.
So what do you think is the role of curation in all of this? The idea that you've got experts that are deciding what to keep and what to throw away and how to organize it, or do you think it can be more automated?
I think curation is vitally important. I mean, my own personal opinion is that some of the data that we're talking about here is really a national trust. It's something of historical and really enduring value. And so the value propositions around data need some sort of forum or vehicle to move forward, because certainly the idea of saying every bit is important as every other bit is probably not helpful, overall. And so I count myself as among the people who used to think that curation was really boring, but actually it's pretty interesting area. And one route toward that's hinted at here is metrics on data access and on the value of data. So if you, David, want 500 terabytes of my data, and you can tell me either definitively or give me a hint that you might do something really valuable with it, right? I should be incentivized to provide that data to you along those sorts of means. But if we're not monitoring that and we're not capturing it, then I doubt we can make those decisions that way.
All right, any more questions?
All right, thanks.
Thank you.